Welcome to week number 5 of the Marlowe Pioneer Program. My name is Yves. I'm working for IOG in the Marlowe team. In the team, I'm in charge of providing expertise for modeling financial contracts. I took over the implementation of the Actus framework from my previous colleague, and I have started Marlowe Contracts, a combinator library for building Marlowe contracts. It also contains helper functions and a collection of well-established financial contracts written in Marlowe. Today, I would like to give a short introduction of financial contracts, in particular derivatives. Then we will have a look at Actus, a taxonomy of financial products. In the second part, I would like to show you concrete examples of financial contracts implemented in Marlowe. Financial contracts are mutual agreements between parties about future cash flows. A domain-specific language for financial contracts must allow to formalize a financial agreement unambiguously in order to do pricing, risk management, and allow to deploy the contract onto a blockchain. Financial contracts can be complex, but complex financial contracts are usually built out of simpler ones, as we will see later. A DSL for financial contracts leverages composability to model complex financial structures. Before diving into financial contracts, I would like to recap the desired properties for a DSL for financial contracts. A domain-specific language is a language tailored to a certain domain, in our case finance. The language should allow, and on the other hand constrain us to unambiguously express meaningful financial contracts. With the combinators of a DSL, we can build a structure that represents a financial contract. With Marlowe, we build a tree structure with closed contracts in the leaves. The other constructors of the Marlowe language make the tree grow, as they all take a continuation contract. The Marlowe language allows closing a contract. It has the pay constructor, the if for branching. With the when constructor, we wait for actions. Let is used to bind values to a value ID, and there's a constructor for assertions. An earlier version of the Marlowe language had an additional constructor called both, allowing concurrent composition of contracts. The constructor both has been removed from the core language, as it can be expressed by other combinators. How this is done is not immediately obvious, but we make use of the fact that the when constructor takes a list of actions as argument. Merging two contracts together, the list of actions for the merged contract has to be constructed to include all the required combinations of actions and continuations. And timeouts have to be considered carefully. The slide shows the code, how this is done in the Marlowe Contracts library. As a side note, the construction of contracts in this manner imposes a big increase in size of the structure of the contract. In order to handle the exponential growth of the contract, we use techniques like Merkleization. I will explain Merkleization later. The Marlowe DSL is a minimal set of constructors. Together with additional combinators like both, we are able to describe complex financial contracts. With syntactically well-defined contracts, a lot of questions arise. For example, is money preserved by the contract? What is a given contract worth? What is the risk that I take when I engage in the contract? These are about the interpretation of a financial contract, the semantics of the language. The execution semantics of a contract are defined by future cash flows. With Marlowe, we have formally verified execution semantics. For example, there is a proof in Isabel for money preservation. Also, the reduction semantics of a contract have been proved correct. The valuation semantics are based on the projected cash flows in conjunction with a market model. The valuation semantics allow to give an answer to the questions about the price or risk characteristics of a contract. For pricing, we distinguish between contracts where analytical formulas are known and others where only numerical methods are available. An influential publication that highlights the similarities between financial contracts and functional programming and introduces syntax and valuation semantics for a DSL for financial contracts is the paper published by Simon Peyton Jones and Jean-Marc Ebert with the title How to Write a Financial Contract. I can highly recommend having a look at this publication. You'll find the link in the PDF in the slides. Financial contracts are mutual agreements between parties about future cash flows. The future cash flows can depend on observables like exchange rates, prices of assets, or an input for choice provided by a party. Let us now have a closer look at financial contracts, derivatives in particular. A derivatives contract is a financial contract that depends on an underlying asset. Its value is derived from the value of the underlying asset. We will look at options and option strategies. These are more complex contracts built by combining two options, for example, straddle, strangle, or call spread. After that, we will also look at futures and other derivatives. Options, Futures, and Other Derivatives is the title of a famous book by John Hall explaining these financial structures in great detail. Let's now start with options. An option is defined as follows. A call option is the right, but not the obligation, to buy an underlying asset, U, at the expiration date T for a fixed price, the strike price K. On the left-hand side, there's the price chart of the underlying asset U. The horizontal axis is the time, and the vertical axis is the value of the asset U. The strike price K and the maturity date T are shown in the graph as well. They are both fixed when the contract is created. At the expiration date T, the holder of the call option can decide if she wants to exercise the option and buy the underlying asset for the strike price K. In case the price of the underlying asset is higher than the strike price, as in the graph on the left-hand side, we say the option is in the money. A holder of the option exercises it and gets the underlying for the price K. The payoff for the call option in that case is the difference of the price of the underlying at capital T and the strike price. If the price of the underlying asset is less than the strike price, we say that the option is out of the money and the contract expires. There's no payoff. The two scenarios can be summarized in the payoff formula. Payoff equals max price of underlying U at capital T minus strike price, or 0. The diagram on the right-hand side shows the exchange of the underlying at time T for the price K. The buyer has the choice to exercise the option or not. In the diagram, a European option is shown. For an American option, the buyer can exercise the option up to the expiration date T. The buyer has to find the optimal time up to the expiration date for exercising the option. This graph is about call options. Let's figure out how this looks for puts. For put options, in the upper diagram on the right-hand side, the arrows at maturity are reversed. That means at maturity, the buyer of a put option can decide if she wants to sell the underlying U for the strike price K to the issuer. Acquiring an option has a cost, as you're getting the right to exercise it. The price of an option is called the option premium. I added the payment of the premium as an additional cash flow at time 0 to the diagram. The chart of the contract reflects the primary market. The primary market is when a contract is issued. The secondary market is where an active contract is traded sometime after it has been issued and before the expiration date T. Options are mostly traded in the secondary market. In the payout diagrams at the bottom, the payouts for call and put options at maturity are shown. On the left-hand side, for the call option, the purple line is the payout as in the formula on the previous slide, with the addition of the premium. If the option is not exercised, the premium is lost and the total profit is negative. The payout diagram shows the profit and loss, or P&L in short. The blue line represents the P&L for the issuer, which has to be symmetric with respect to the x-axis to the purple line, as the contract preserves the money. The sum of the blue and the purple payouts is 0. We usually refer to the buyer as a long position in the contract and the seller as short position. The options long call, long put, short call and short put can be combined to build more complex contracts in order to model a desired payout function. Option strategies. The diagram on the left-hand side shows a call spread. A call spread is a combination of a long call with strike K1 and a short call with strike K2, both with expiration date T. This results in the red line, a bounded payout both from below and from top. That means it limits the loss but also caps the gains. There's a linear increase between K1 and K2. The diagram on the right shows a straddle, a combination of a long call and a long put, with the same strike K and the same expiration date T. The result is the red line, a V-shaped payoff which is negative around the strike price K. Both of these examples are combinations of options that are combined concurrently. We will see these examples later in the code as well. There are many more well-established option strategies like the two mentioned here, but let's now have a look at covered calls, as they introduce us to the topic of collateralization. A covered call is a combination of a call option on an underlying U in conjunction with the underlying U. The issuer of the contract has to provide the underlying into the contract when the contract is issued as a collateralization. That means that the option contract is covered with the underlying, and in case the buyer exercises the option, the underlying is already present in the contract to be transferred to the buyer. Compared to the plain option, here we are sure that the delivery can take place, as the option is covered. A full cover of the underlying is the simplest technique for collateralization. There are other techniques to collateralize a contract, for example margin calls for future contracts. A future is the obligation to buy or sell an underlying asset U at the delivery date T for a fixed price K. Futures as well are mostly traded in the secondary market, and therefore a future is assigned a price during the lifetime of the contract. In many cases, the delivery at T is not physical. That means only the change of the difference in value between the two assets is transferred. In order to ensure that both parties are able to fulfill their obligations, futures are set up with margin accounts. A margin account is a deposit that both parties have to maintain. In case the relative value of the two assets changes over time, the exposure in the margin account needs to be adjusted. This is done by periodically checking the margin requirements and issuing margin calls to increase the amount of an asset in an account to meet the requirements. In case there is no deposit following a margin call, the contract is liquidated. Having margin requirements is another form of collateralization, a way to ensure that the obligations of the contract are met. So far, we have seen options, futures, combinations of options, and also a combination of an option with an underlying. But there are a lot more other combinations of smaller contracts to build larger ones. Let's summarize those as other derivatives. Other derivatives could, for example, be a combination of a zero coupon bond and a short put option. By selling an option, the contract can pay out a premium. This is usually called a coupon payment. And on the other hand, the option is collateralized by the face value of the bond. That means the contract can buy the underlying when the put option is exercised, as the strike price for the option is set to be the face value of the bond. Another large class of products are built with path-dependent options. A path-dependent option is an option for which the value depends not only on the price of the underlying asset, but also on the path that the underlying asset took during the life of the option. There are many types of path-dependent options, for example, barrier options. A barrier option is an option that comes into effect if the underlying breaches a fixed barrier. For this example, we require an oracle to provide the value for the value of the underlying. The financial industry loves to compose contracts like in the examples above in order to model a desired payout.